No, that's great. So yeah, thank you very much everyone for joining us. So welcome to 2022. Let's see how this year goes. What am I going to speak about today? I'm going to speak about oscillatory reconnection, which you should think of as a relaxation process, a time-dependent relaxation process. A time-dependent reconnection process that also has wave generation properties. Okay. So what are we talking about? Well, we're obviously talking about reconnection. So what is reconnection? This should be familiar to most people. It's a fundamental plasma process. It's a way of changing magnetic field line connectivity. So you can see the simple cartoon at the top. A is connected to B. The reconnection process occurs, and now A is no longer connected to B. A is connected to C. So this is a method to change the magnetic topology, but it also does lots of weird and wonderful things. So it converts stored magnetic energy into heat and kinetic energy, and it's also a mechanism for accelerating fast particles. And it's an absolutely fundamental plasma process that is at the heart of a majority of solar phenomenon. So think about solar flares, CMEs, coronal heating, all of those things. And essentially in 2D, it's very well understood. You can think of it as this little cartoon at the bottom. And remember, it's all about that change of connectivity. So a red field line and a blue field line coming from the top and bottom. And then at the cross there, so think of that as the X point, they join together, there's a change in connectivity, and then a combination red and blue go off to the left and right. You can also see the same with the green and the purple. And like I said, it's very well understood in theory, but actually it's very well understood in a steady state setup. So you can see from the cartoon here, blue and red coming in, green and purple coming in and going out. But actually this is a steady state process. The process has been set up, it's going on forever. And obviously what I'm showing here is a 2D cartoon. And so we already have a little problem. And that little problem is, on the previous slide, I said reconnection is fundamental to many solar events, so flares, CMEs, and here we're really being presented with steady state theory. But actually what we really need is time-dependent theory, because of course a solar flare is a finite duration event. A CME is a finite duration event, and therefore steady state theory might not be quite as applicable as we want. And so we need to move our theories forward into a time-dependent theory. So that's a bit about reconnection. What about waves? Well, essentially, I've been interested in waves around null points for a long time, and I'm presenting here a simple example. So let's consider a 2D simple X point at the bottom there. So you can see the magnetic field lines. You can see those special red field lines there forming a cross. Those are the separatrices. They cross at the origin, which we're going to call the null point. And it's commonly called an X point because it looks a lot like an X. We're going to send a wave in from the top boundary, and we're going to see what happens effectively. And so this is what happens. So the wave comes in. Oh. So this is the little setup here. Wave comes in from the top boundary and it wraps around the X point here. So what you're seeing here is a numerical solution, is the colored contours, and you're also seeing an analytical solution, the WKB solution, as the white lines there, and it wraps around that null point. And if I just reverse this maybe, so the wave comes around and it wraps around that null point there, and just continues that wrapping. So how do we understand this? Well, actually, we can write down the MHD equations. So that's what I've got in the red box there. I'm going to solve them using the layer 2D code, a Lagrangian remap code. That code is ideal for solving shocks, which will be important later. So I can write down my MHD equations. I could do a lot of simplifications. So what I'm going to start with is an ideal plasma, a cold plasma. So beta is equal to 0. And then I get lots of cancellations. I'm going to study a linear system to start off with. And I get those cancellations there. And I recognize that there's a natural variable to the system. And that variable is related to V cross B. So it's related to the perpendicular velocity. And I'm going to call that sigma. And if I sub that in, then my equations reduce to the following. They reduce down to that single wave equation there in the red box. So dt squared of sigma on the left, and then a spatially varying speed on the right. So that's the alpha in speed here, VA. It's obviously related to the magnetic field. And here VA is just equal to R. So it's just equal to the distance away from the null point. And so that explains our results, okay? So when we have a linear fast wave, it travels towards the vicinity of the X point and it bends around it. So it demonstrates refraction. That wave is wrapping around the null, and it's doing that because essentially the alpha speed is spatially varying. It travels faster the further it is away from the null, and it travels slower the closer it is. And it cannot cross the null point in this system because, of course, the speed is going to 0. And so the reference there is in the yellow box at the bottom. And this is a key feature of fast wave propagation in a linear and cold plasma. So we have this system where we're wrapping around a null point, and it's obvious then that that spatially varying speed plays a key role. So it's natural to consider the whole system in polar coordinates or with a circular pulse, a circular initial condition. So now let's set up a similar system, but with this red circle as our initial condition. This is going to start, when the system starts, that's going to split into 2 waves, an incoming wave, so a contracting annulus around the null point, and an outgoing wave. Okay, it's just D'Alembert solution, it'll split into 2 waves, and we're really interested in that incoming wave. But we already know what will happen because we already know that the speed will vary as r, as the radial distance. That speed is decreasing as you get closer and closer to the null point. And so our wave will get slower and slower as we approach the null point. And you can see that here. So for a linear cold fast wave system with that circular initial condition, you just have a contracting annulus that comes around and contracts around the null point. Not a very interesting system, but well understood. What's more interesting is when you increase the amplitude. Okay, so if we increase the amplitude, we can get to a non-linear system. And when we get to a non-linear system, the following happens. So I'll play the movie. And we get a fundamentally different system. So quite a psychedelic system. You can see time increasing at the top. And essentially we're getting oscillation of that X point. Okay. So I'll step through those slides because it's a complicated system. So remember what we've got. We've got our circular initial condition. We have our X point, we have our separatrices, which go through 45 degrees. And we set off our initial condition at radius of 5. And what I'm showing on the screen here is a box from -2 to 2. Okay, so when the simulation starts, the wave is outside. I'm showing you a subset of the system. And so that wave should be coming into the system. So as I step through the time, you can see the wave coming in. But because I'm stepping through, I can stop it at certain times. And you can see that the system is starting to display nonlinear behavior. So this is a contracting annulus, as we expected, but you can see fundamental differences. So here is a fundamental difference. This wave is starting to shock, and shock waves bend magnetic field lines. This is a fast shock, and so it refracts the magnetic field away from the normal. And you can see that here. You can see it bending the separatrices. So remember, the null point is here. It's called an X point because of this X point structure. And so if I follow a separate frequency out, it's unperturbed until the wave has crossed it. And so the wave refracts it away from the normal. And so you can see that it no longer goes out at 45 degrees. That magnetic field has been fundamentally changed by the passage of that shock wave. You can also see that this shock wave is shocking on the leading edge here as it comes in, and the leading edge here. But actually, at the sides, it's shocking on the trailing edge, which you can see here, and you can see here. It's much easier to see it when you do cuts. But again, you know, that's a fundamentally different behavior. So shock waves are forming, and actually quite non-intuitive shock waves here. We're used to waves shocking on the leading edge, but here it's shocking on the leading edge above and below, and shocking on the trailing edge to the left and right. So if I continue to step through the system, so the wave comes in, you can see it perturbing the magnetic field. At a certain point, the shock waves start to overlap and they form jets. And then as I click through, you can see at this point, the waves have reached the null point and they have perturbed that X point. So it's still a null point because the magnetic field at the origin is 0, but you wouldn't describe this as an X point. Okay, this is more like a cusp point and the magnetic field has been perturbed. And then what happens later is the system collapses into a horizontal current sheet, which you can see better perhaps at this time here. And so we've moved from that X point to a horizontal current sheet. Okay. There's lots going on in the system. At earlier times, you can analyze those fast shocks we spoke about, those fulfill the shock conditions. You can also analyze the jets that are occurring at the side. So if you can do if you zoom in and do cuts, you can see that it follows the reconnection jet explanation of Terry Forbes. And so you have what he described here as the X line, Petschek shocks, termination shocks, and deflected shocks. And so we've successfully set up a horizontal current sheet in our system. Remember, it's a dynamic process, so this thing is changing as time goes on. And what I'm presenting here is just the time slot, the time slice at time equals 4. What then happens at a later time, let's say time equals 7, is the system forms a vertical current sheet. So just to go back one slide, at time 4 it was horizontal, and at time 7 it's a vertical one. So if you were very quick, you could see that in the movie, but now I'm just stepping through some of these time slices. At a later time, then it forms a horizontal current sheet again. That, of course, is the third horizontal current sheet in the system because it was initially horizontal, then it was vertical, then horizontal, then vertical, and this one here is horizontal. And actually, if you look at the current at the origin, you get an excellent tracer of this. And so you can see JZ oscillating up and down there. Whenever it's negative, that's the formation of a horizontal current sheet. And whenever it's positive, that's the formation of a vertical one. So I've put little red and blue dotted lines on there so you can see. But essentially, you go through a pattern of horizontal, vertical, horizontal, vertical, horizontal, vertical, and so on and so on. The amplitude gets smaller, which means the current sheets are getting shorter. And you can see there in the little insert, I've zoomed in, but you can see this thing is oscillating up and down. It also oscillates about a constant value, and that JZ is 0.862 for these particular conditions. And that's because at the end of our simulation, the system returns to equilibrium, but a very slightly different equilibrium. And that's because the system is hotter, slightly hotter on the left and right than above and below. And so the system is very slightly scissored up, if you think of it like that. And that's why it tends to a constant value, which is that green line that you can see there. And so it's clear we've got oscillatory behavior. We've got an oscillation about an equilibrium. we've got positive and negative values of JZ. And essentially that's where the oscillation in oscillatory reconnection comes from. So it's clear we have an oscillation. Do we have reconnection? Well, there are different ways to measure that. One qualitative way is to trace the field lines, and that's what I can show here. And so essentially I've traced red field lines into one domain of connectivity and blue into the other, and they're separated by those black lines, which are the separatrices. And at a later time, when we're forming that horizontal current sheet, you can see you have more red field lines on the left than compared to above and below. And these are tracing the same field lines as before. At a later time, when we're starting to form a vertical current sheet, we have more blue field lines on one side of the separatrices than the other. And at the end of the simulation, we have more blue field lines on one side than red on the other. So that's a qualitative measure of tracing them. The other quantitative way is to track the reconnection rate, which is related to the time derivative of the flux function. And that shows very good agreement with the JZ profile that I showed you, essentially this oscillation back and forth. And so we are getting reconnection, but we're getting time-dependent reconnection. Flux is being exchanged from one connectivity domain to the other, but in a continuous way, being swapped between them. All of that is described in the paper in the bottom right, so a paper from 2009. So I tend to put my references in these little yellow boxes if you want to make a note of those. And remember, this is for a two-dimensional cold system. So the system starts at temperature 0. As the shock waves come in, they naturally heat the plasma. And so even though it starts at beta equals 0, the system refuses to stay cold and generates its own heat. But this is a two-dimensional system around that two-dimensional null point that describes oscillatory reconnection. The process also works in 3D. So you can see a different reference there in the top right. So this is the description of 3D oscillatory reconnection. Reconnection in 3D is more complicated than reconnection in 2D. The null point here has a spine and a fan. And what we're getting here when we perturb this three-dimensional null point is spine fan reconnection. And you can see that in the little pictures at the bottom. We're getting spine fan reconnection where the where essentially the fan sweeps over the spine, but we're getting this in a time-dependent manner. So I've called it three-dimensional oscillatory reconnection. You could also call it oscillatory spine fan reconnection. Again, you get the formation of, you get this exchange between the two domains of connectivity. And essentially you can think of it as, well, you would no longer think of it as horizontal going to vertical, going back to horizontal and vertical. You can think of it as different orientations. Let's say orientation 1, orientation 2, orientation 1, orientation 2. So that's the description of oscillatory reconnection in 2D and 3D. Both of those were set up for, let's say, simple X points, so well understood geometries, and we have a lot of control over that system. You can also perturb X points in different ways. And one of the, so essentially what we've done before is we've hit this thing with waves. And so, you know, remember at the start, I described a system where fast waves are attracted to null points. They wrap around them and they form this sort of quasi-circular behavior. And then we've investigated that in 2D and 3D. But actually, perhaps oscillatory reconnection is more fundamental than that. And perhaps this is to do with perturbing X points in different ways. And one of the ways to do that is flux emergence. So what is flux emergence? Well, we know that magnetic field is continuously emerging on the sun over a range of scales. And essentially, what we're talking about here is burying a magnetic flux tube that rises buoyantly through the solar interior until it gets to the photosphere. And when it gets to the photosphere, that buoyant rise ends. And then the magnetic buoyancy instability kicks in, and that allows flux to penetrate into your atmosphere. So what we're seeing here is a initially uniform vertical magnetic field with a buried flux tube here. That flux tube is in radial force balance, it's in thermal equilibrium, but there's a density difference. And so the flux tube buoyantly rises relative to its surroundings. It hits the photosphere, it penetrates the photosphere due to the magnetic buoyancy instability, and it emerges into the solar atmosphere. And that's what you can see in these little time slices at the bottom. This is it emerging into the magnetic, this is it emerging into the solar atmosphere, which has a pre-existing vertical magnetic field. And this, literally flux emerges into the system and it clashes with the pre-existing magnetic field to form this current sheet that you can see here. This system emerges, and at some point that emergence stops. And once that emergence stops, then the oscillatory reconnection process kicks in. So oscillatory reconnection is a relaxation process. It's the null point trying to recover its initial configuration via reconnection. When flux emergence is going on here, when the flux is penetrating into that pre-existing field, that's a driven system. And so you're not going to get oscillatory reconnection until the system is not driven, until the system no longer has a forcing. So essentially it penetrates in, it forms that current sheet, and once the system is no longer rising, then you can get the relaxation going on. So flux emergence is very well understood. There are many, many models, many different setups. So the oscillatory reconnection manifests really at the later time scales of this. Remember, it's all to do with that emerging flux compressing that pre-existing magnetic field. You get the current sheet formation, and then at later times, this is what you're seeing. So you get this current sheet formation here, and at a later time, the current sheet has this orientation, then this orientation, then this orientation. So before, if we were calling this horizontal, then this would be vertical, goes back to horizontal, goes back to vertical. Of course, horizontal and vertical don't really mean anything here, so we'll just call them orientation 1 and orientation 2. And again, it's that exchange, orientation 1 followed by orientation 2, go back to orientation 1, back to orientation 2, and so on and so on. This is a more complicated system, but more physically motivated in certain aspects. And what we need to do here is track that null point, because of course it's rising through the system. It occurs at different altitudes. And we can do that by measuring the flux function. And what we did here is we investigated different values of the magnetic field strength, specifically of the initially buried flux tube. And we found that for these 8 values we investigated, we got flux emergence in each one, it penetrated into the atmosphere, and we got oscillatory reconnection present in all of those systems. But depending on the magnetic field strength, we got a different period. So for these initial conditions, for this magnetic setup, we could recreate periods of 105 to 212 seconds. Okay, and there's a relationship there between the magnetic field strength and the resultant period of oscillatory reconnection. What's interesting as well is we found an upper bound and a lower bound for our system. We found a lower bound because it would be natural to say what happens as the magnetic field gets weaker and weaker. And there's a lower bound because if your initially buried flux tube has a low magnetic field, you get failed flux emergence. And you get failed flux emergence because as you bodily rise, you hit the photosphere, and if you are below the magnetic buoyancy instability, you don't penetrate into the atmosphere. And so that's what's called failed flux emergence. And so that led to a natural lower bound on our system. Conversely, if the magnetic field strength of the buried flux tube was let's say strong, if you think of it like that, then you got flux emergence. It rose at a greater rate, it penetrated to a higher altitude in the system, and it created a longer current sheet. And what we got there is the presence of the plasmoid instability. So we could form X points that had long current sheets, and then they would emit plasmoids during the reconnection process. So the plasmoid instability is also known as the nonlinear tearing instability, and that's where your magnetic field reconnects. But if it fulfills certain criteria, you get the ejection of a plasmoid. And that's what we could see in our simulations here. But actually, once you eject a plasmoid and then you get the oscillatory reconnection process afterwards, it's a fundamentally different system. And so we viewed that as an upper bound. And so what was nice about this flux emergence example is we got oscillatory reconnection present for a range of magnetic field values, but we had a natural lower bound and a natural upper bound. All of these numbers could be changed as well, depending on the strength of that vertical magnetic field and the plasma properties. Here's some more recent work that I've been doing with my postdoc, Karampoulos. So Karampoulos, McLaughlin, both at Urania. So it's accepted in AppJ, so it should be appearing very shortly. And what we did here is we went back to our two-dimensional X-point system, and we investigated oscillatory reconnection in a 1 million degree plasma. So actually the paper varies the temperature, but what we did is we extended that 2D model I showed you before, which was initially cold plasma, and we extended it to a 1 million degree plasma. So it was the first demonstration of that. And you can see the results on the right. We get oscillatory reconnection oscillating up and down when we look at JZ. What was interesting as well is we did this simulation using the Pluto code. And so all the simulations I've shown you up to this point have been done with the layer code, which of course was that shock capturing code. So it was interesting or reassuring to see you could get the same same effects using the Pluto code, so using a different code. So this paper shows that oscillatory reconnection is not code dependent, if you think of it like that. What it also did was it included anisotropic thermal conduction. And so thermal conduction is present in the solar corona. It's clear we're generating heat. And I guess I wondered if thermal conduction would suppress or kill the process. And the answer is it doesn't. So including thermal conduction doesn't prevent the oscillatory reconnection mechanism from manifesting, but it does increase the decay rate of the oscillations. And if you look at the force balance that's causing this relaxation, that makes sense. And you can read about that in the paper. So what we can see here on the right is an oscillation of that null point. So you can see the oscillatory reconnection process. You can also measure the periods of these things using a wavelet, for example. And you can see that this has quite a well-defined period, just lower than 5 there. So let's say 4.5 or something. And it has quite a well-defined duration. And remember, of course, these are all finite duration events because we inject a finite amount of energy into our system. Our X point oscillates. It's not surprising we get a finite oscillation that comes out the other end. I've also presented this here in code units. So if you think of the period as approximately 5 and it lasts for approximately 20 code units, think of these as Alfvén times. So for the particular setup here, the Alfvén time was about 8 seconds. And so you're talking of a period of about approximately sort of 40 seconds. What that paper also allowed us to do is to vary the strength of the equilibrium magnetic field. And we found an inverse relationship between magnetic field strength and the period of oscillation. So the period of oscillatory reconnection. And that's what I've presented on the right there. So I've shown it as the of the inverse of the period, and you can see that straight line fit. And so we found that stronger magnetic fields correspond to shorter periods of oscillation. Or conversely, weaker magnetic fields oscillate for a longer period of time. We also found a relationship, so a linear relationship, between magnetic field strength and the decay rate. And so what we found is that for stronger magnetic fields, the system is restored at a faster rate. So for stronger magnetic fields, the decay rate increases. And both of those results are interesting because it allows us to then start relating period and decay rate to magnetic field strength. And both of those results, so stronger magnetic fields corresponding to shorter periods and strong decay, can be thought about by considering, let's say, the stiffness of the magnetic field. So stronger fields are more resistant to deformation, and once they're deformed, they relax back to equilibrium at a faster rate. And so what that really does is it opens up the tantalizing possibility of utilizing oscillatory reconnection as a seismological tool. Obviously, it needs more study, and these are early results, but I'm very excited by that idea. Okay. So what have I described? I've described a time-dependent reconnection system. That system is wave generating, although I haven't really spoken about that too much today. But the system generates waves. So for the two-dimensional system, it can generate fast waves and slow waves, or more accurately in the system, it generates a Vx and a Vy, and then the system reacts in a certain way to create the waves from that. And in 3 dimensions, it generates a Vx, Vy, and a Vz. The big difference in 3D is you can generate the alpha wave, which is born with a rotational property. And different authors have then picked up on the time-dependent reconnection and the oscillatory reconnection process and have started to invoke it as an explanation for different phenomena. So I'll just put the list there. That first paper there was investigating periodicities in an active region correlated with type 3 radio bursts observed by Parker. So that's in a fantastic paper by Cattell et al. Last year. It's also been used to describe a new type of jet in a solar coronal hole. If you think about that flux emergence example I was showing for that vertical field, you could use that to describe a coronal hole. It's been used to describe oscillations of small H-alpha surges in a coronal hole. It's been used for the formation and disappearance of a flux rope in data from the New Vacuum Solar Telescope. It's been used in observations of the reversal of breakout reconnection. The system I'm describing is clearly related to breakout reconnection. And finally, I just wanted to bring your attention to a paper there about rotating network jets observed by IRIS. Oscillatory reconnection, which I've written as OR there, is also explicitly mentioned in the science requirement document for EST. That's the European Solar Telescope, in section 6.5, if you want to go and have a look. And so oscillatory reconnection, essentially what I've described so far is different investigations. And now we're starting to apply it to solar examples. So here are some examples there. But what I wanted to start to bring us to the end of the talk and talk about is relating it to quasi-periodic pulsations. Okay, so what are quasi-periodic pulsations? Well, they're related to flares. So if you think about solar flare emission, it's detected in all electromagnetic bands, variations in flux density, But often, and I might even say the majority of times, that radiation is generated with a pronounced oscillatory pattern. So it's got a characteristic period from fraction of a second up to several minutes. And those oscillations that appear in that solar flare radiation are referred to as quasi-periodic pulsations, or QPPs. And they're a key observational feature of the emission of solar flare energy. Okay, this pronounced intermittent pulsation. And you can see an example here. So at the top, we're showing a QPP for an X4.9 flare. We've got GOES data and RESI data and Northumbria data and LIRA data. And then in the three subpanels below, we show RESI data, the Northumbria and LIRA data, but detrended. So we've extracted a trend from that, and you can see the oscillation in each one. And they're remarkably synchronous between each other. And so you have an oscillation here that's being observed by different instruments. So it's not an instrumental effect. It's also being observed across different energy bands. I've talked about QPPs there related to solar flares, but actually they've been detected in stellar flares as well. So XMM Newton data, Galax data, Kepler data, which became K2, all of that have detected QPPs in stellar flares. So we have many examples of QPPs in solar flares and stellar flares, so hundreds of examples. And there's so these are not sort of rare events, they're occurring in the majority of solar flares, perhaps even in the majority of stellar flares, but of course our techniques to measure them vary for stellar, for stars. But what's interesting there is they're a key feature of this energy release. And so QPPs are directly linked to the energy release and transport processes occurring in flares. And so their observational characteristics are an important source of information about the flare physical process. And so what we really want to do is, I guess, at a period of time, we were discovering QPPs, and now we have hundreds of examples. And so the attention has turned to what is the correct underlying or underpinning physical mechanism. And what we want to do is pinpoint that correct mechanism or mechanisms, because the occurrence of QPPs puts additional constraints on the interpretation of fundamental flare processes. Or in other words, the correct flare model needs to be able to explain and predict QPPs. So what we're doing is we're working towards this full understanding of QPPs, which is then essential to understand a fully integrated model of solar and stellar flares, as well as advance the solar stellar analogy by looking at other stars. And I wanted to draw your attention to two papers at the bottom there, both in Space Science Reviews, that investigate these different possible underpinning physical mechanisms. And so there are a lot of them there. So let's say there are over 10, and I've listed 13 of them there. You have free MHD oscillations at the top. You have reconnection periodically triggered by external waves. You then have oscillatory reconnection that I spoke about before, and you have different examples. And that McLaughlin 2018 paper at the bottom takes you through all of those potential models, and it investigates each of them and their applicability to QPPs. And more recently, the Zimovitz paper at the bottom again reviews the underpinning physical mechanisms, but really also extends it to stellar flares as well. And what's special about that Zimovitz paper at the bottom is it also makes observational predictions from each of those different underpinning methods. And so it'd be natural to say which is the correct one. And unfortunately, the correct one is still, it's not, it hasn't revealed itself. So we know that QPPs are important to understand because they unlock solar flare physics, if you think of it like that. And oscillatory reconnection is one of the leading explanations. That doesn't mean it's the right explanation, because the underlying physical mechanism or mechanisms are still a mystery. So oscillatory reconnection is one of the leading explanations because time-dependent reconnection would naturally explain the simultaneous nature of QPPs in different energy bands. And that's because the QPPs were being produced by the same cause, which is the time-varying rate of electron acceleration. So I think that's probably where I'll end. So I think I'll go back to that one. And then I think I'll end my presentation next. I see it's got to sort of 40 minutes.